Yeah, it's going to still show up, but I think we'll be okay. All right, so yesterday we finished off with the last problem was we proved that the limit of 1 plus 1 over n all raised to the n was e, right? And then we showed how we could generalize that for any power of e that we wanted. So today what we're going to do is we're going to continue on with that example. I have a couple other sequences that we want to look at, and we want to test them for convergence. So remember, the way we test a sequence for convergence is we look at the infinite limit, okay? And so there's a couple different techniques that we may have to employ, and you'll see for some of these we may not actually have to use the limit at all right? So let's look at, continuing on with our early example, let's look at the sequence n minus 1 all over n. So I can see, good, perfect. All right, so the first thing we want to do is we want to take the limit as n goes to infinity of the sequence. So we have a ratio, so this is definitely, right, we would plug in infinity in theory, and you can see the numerator is going to go to infinity, the denominator is going to infinity, so this is definitely a L'Hopital situation. So the limit, right, is going to equal the derivative of the numerator over the derivative of the denominator, and we just get 1. So we only had to do this one time. So we would conclude that this sequence converges because we got an actual answer. But remember, I told you guys, if we're testing for convergence on a sequence, you need to explicitly state that the sequence converges to 1. So you have to tell me not just that it converges, but what value it's converging to. And for sequences, it'll just be the result of your limit. All right, so let's look at another one. So if we want to look at 5 over n squared. Right? And we'll start by taking the limit as n goes to infinity. So this is not a L'Hopital situation, right? But we also looked at, when we talked about L'Hopital yesterday, we also looked at what do you do when you have a constant over infinity, because that's what you're getting here, right? 5 is 5, infinity's on the denominator, so what do we say the result is then? 0, right? So we all learned in Calc 1 that the limit as n goes to infinity of 1 over x, or excuse me, the limit as x goes to infinity of 1 over x was 0. So it stands to reason, right? That's just 1 over n times 1 over n, so you're literally just getting 0 times 0. But now we don't have to go back to first principles and show everything from first steps. So now I would interpret that as, well, that's just clearly 5 over infinity. And I know that's going to go to 0, right? Because we said any constant over infinity. So we would conclude that this sequence converges to 0. All right, let's look at one more. So we have 4 minus 7 n to the 6 over n to the 6 plus 3. So this is a polynomial over a polynomial. So if we set up the limit this is definitely an infinity over infinity situation. So we could take L'Hopital. That's a totally legitimate method to figure out this limit. But if you're in a situation where you have a polynomial over a polynomial, we learned back in Calc 1 that even if I had like a n to the 4th and n, if I've even had more terms in this polynomial, that the highest power is going to dwarf all the other powers when you're looking to infinity. So if you raise something to infinity to the 6th, that's going to just mean nothing to infinity squared, right? So another way you can do, rather than using L'Hopital to solve this limit, is you can say, well, this limit is equivalent to the limit of the highest term in your numerator over the highest power term in your denominator. note that you do need the coefficients. They matter. So we had to say negative 7 into the 6. So now you can see that these into the 6 cancel, and we get negative 7. So this sequence converges to negative 7. So furthermore, we could see, well, these powers were equal in the numerator and the denominator. So sometimes if people are really good at infinite limits, like I actually knew looking at the original thing, I was like, oh, we're going to get negative 7 over 1, right? If the excuse me, if the highest power of the polynomial in the numerator is greater than the highest power of the polynomial in the denominator, everything's going to blow up to infinity because the numerator is going to grow faster, right? If the highest power in the denominator is bigger, then we know the denominator is going to outpace the numerator and everything's going to go to 0. If the powers are equal like this, we see we just get the ratio of the coefficients of those two guys. So this is another valid method when you're taking a limit to infinity. Yeah.
So if there was 4n minus 7 plus 3x.
I'm sorry, say it one more time.
If it was like 4 times n minus 7 and 6.
Yeah, so what you're asking is if the 4 had an n attached, right, and then we maybe attach an n to the 3 as well, it would still be negative 7, right? Because you're only going to pack, because if we had 4n minus 7 into the 6, that n to the 6 is just going to outdo that 4n. That 4n will just become completely insignificant. Because remember, this is only true when we're going to infinity. I mean, we were talking about incredibly big numbers, right? So if you just look at 2 to the 6 compared to 2, right? 2 to the 6 is what, 64, right? That's enormous compared to just 2, right? 2 to the 1. So when you start increasing 2 to like infinity, right, you're going to see that difference become even bigger. So, and also look what would happen if we actually did L'Hopital here. If we did L'Hopital, the numerator would be what, negative 42 into the 5th, and the 4 would go to 0, because the derivative of 4 is 0, right? And then the denominator would just be 6 into the 5th, and the 3 would go to 0. And so then the into the 6 or into the 5ths would cancel, and you would end up getting negative 42 over 6, which is in fact negative 7. So you would still get the same thing. Dylan, do you have a question?
What if the top numerator was like a large number and the bottom number was vice versa?
Right, that's what I said. If the numerator, if the power in the numerator is bigger, it goes to infinity because the numerator is blowing up faster than the denominator. If the denominator has the bigger power, the whole limit collapses to 0 because the denominator is growing faster. Okay? All right. So let's look at some properties that we can apply to limits. So these were just very basic, straightforward sequences. We were able to compute the limit directly. But just like anything we do with limits, right, we want to get creative. So we can add, subtract, multiply things. So let's look at the algebraic properties of the limits of sequences. Okay, so there's a couple things we can do. So before we get started, let's let the limit of some known sequence a sub n equal L, and then let's have a second sequence that we'll call b sub n, and its limit will be k. So now, given that those two things are true, and so this is important. What we're saying is both of these sequences converge, right? Because their limits exist. So if I want to take the limit of the sum or difference of two sequences, well, we know from our properties of limits, we can take the limit of a sub n separately from the limit of b sub n, and so our result will just be L plus or minus k. So some of these properties are going to seem pretty obvious because they're an extension of the normal limit operations we're allowed to use. All right. Similarly, if we throw a constant into the mix, so so some known constant C times our sequence, well then I'm allowed to pull that constant out front. So then your result would just be the constant times the original limit. If we multiply two sequences together, well then I'm allowed to take the limits individually and then multiply their results. So this was a property that we learned back in Calc 1, and what we used to say was the limit of the product equals the product of the limit. All right, so some of you may have a guess of where the next one's going. We can also divide them. So if you want to put one limit over another limit, we can say, well, it's the limit of the numerator divided by the limit of the denominator. So we would get L over K. Now there's one extra caveat to this, right? Whenever you're dividing something, we're not allowed to have 0 in the denominator. So there's a condition on this. K cannot be 0, and the sequence itself in the denominator cannot be 0. So we are going to talk about a little bit later that you can have a sequence that's just a constant number, right? So if I had the sequence of b sub n equals 0, it would just literally be 0, 0, 0, 0, 0, 0 for infinitely many zeros, right? So it doesn't really make a lot of sense to have a sequence that's just a list of one number, but later when we get into series, you'll see that, you know, we may or may not want that to be the case. All right? Everybody good? Okay. All right, so let's look at a sub n equals 1 over n. So let's actually look at what a sequence looks like. So just like everything we do, there's an algebraic interpretation and then there's sort of a graphical interpretation. So sometimes if the sequence kind of looks like a function that you've played with before, we can actually plot the points on a graph. But what's going to be interesting is what numbers are n allowed to be? When we plug into sequences? Integers, right? But if I wanted to compare this to the function f of x equals 1 over x, well, I'm only going to look at the portion of f of x where you plug in positive x values, because we want to compare the structure of this to the structure of this. So I only really want to look at the part of this that lives in the first quadrant, right? So if I'm graphing this, 1 over x, when you plug in values above 0, looks like this. So if we actually plot points, though, for 1 over n, well, remember, we usually start at 1. We certainly can't plug in 0 into that because you can't get 0 in the denominator. So if we plug in 1, we're going to get 0.11. If we plug in 2, we're going to get 1/2. If we plug in 3, right, we get 1/3. And I'll go one more. We get 1/4. So notice that the values in the sequence live on the line of the function, right? But the sequence are just integer values, so all you're getting are points, right? where the function would allow for any value of x in between 1 and 2 and 2 and 3 and 3 and 4. So if a sequence kind of looks like a graph that you've seen before and that you recognize, the dots, it's sort of like connect the dots when you're a kid, the dots will form the pattern of that line, and if you connected all the dots, you would end up back at the original function, okay? So we can actually see, if you looked at this function, and we know, because we've done this limit a bunch, we know the limit of f of x as x goes to infinity is 0. Well, here I can actually see that it's going to 0 when I graph the red line. If you look at the dots, we can see they're following that same path, and so the limit is actually going to go to 0. So there is a way to visualize this graphically if you need to. So sometimes just plotting the function that it's mimicking will kind of give you a clue on what's going to happen to the line itself. Does that make sense? Okay. So just remember, a sub n, right, only accepts integer inputs. Right, in the natural numbers, that little funky n, that's all that means, right? And f of x accepts all x that are in the real numbers except x equals 0. So the domain of f of x is any number but 0 is okay, right? And if you want to think about the domain of the sequence, right, it would just be all n values greater than 0. So just 1 to infinity would be totally fine. Yep.
What is that?
So that little n, so whenever we do like the double, see bars here and double bars here on any capital letter, that's called like math script. And what we use it for is this stands for the set of all natural numbers. And the natural numbers are just 1, 2, 3, 4, the counting numbers. They're integers. And R is the real numbers, and that's every number from negative infinity to positive infinity. So it's just like an abbreviation we use for that. Yep. And I had a book, and I remember when I first got to UGA, one of my first arguments with one of my professors was, and I can't remember now which way it went, but in my old school, I literally had to go get the textbook to show him I wasn't crazy, but when I took discrete math, they told us 0 was in the natural numbers, and then I remember in my other book, it was saying no, they start at 1. So it's just kind of an up and down, but we know in this situation, 0 is not even on the table for us. So we're just talking about 1 to infinity. All right, so let's look at more tests for convergence. So ideally, the goal is use infinite limits wherever you can, because it's actually the easiest way to do it. If we can algebraically just compute the limit, we're done, all right? But let's look at those first 4 sequences I showed you yesterday where we actually generated the terms. So let's kind of backtrack a little bit, and let's take a look at this guy again. So it's 3 plus negative 1 raised to the n. And we saw that when we generated the terms of this sequence, it just alternated between 2 and 4 forever. So this is an example. If you actually tried to compute the limit of this, we could do it, but we would have to use the squeeze theorem, which I'll bring that back up later, and we would see that the limit does not exist. But this is an example of a sequence that you can kind of look at it and just go, yeah, this thing's never going to converge, because it's just going to bounce back and forth between 2 and 4 forever, and there will never be a limit. So here, this is a great example of a limit that I said you can just tell like just doesn't exist. We're not getting positive infinity, we're not getting negative infinity, we just can't compute it at all. Right? So there are 2 kind of logical ways to calculate this limit. if you see that it's a polynomial over a polynomial, and that the highest power in the numerator is 1, the highest power in the denominator is 1, so you might just go, that's negative 1/2, and be done, right? If you didn't see that, and you said, oh, well, I see infinity over infinity, then L'Hopital takes you straight to negative 1/2 as well. So just remember there are multiple ways to get there. As long as you justify your method, I'm okay. I just want to make sure I see your work. So, right, we would say this guy converges to negative 1/2. So I'm going to be really annoying about that in sequences. All right, let's look at this guy. So does anybody just know what the answer to this is? No? You see infinity over infinity. What you got? Yes. It will go to 0 because 2 to the n is going to grow much faster than n squared. Okay? But let's just say we don't know that yet. Okay? And you didn't see the answer. And but we know we're going to get 0. Right? Let's say we didn't see that and we didn't know the answer, but you looked at it and you're like, oh, well, that's infinity over infinity. So we can use L'Hopital. But does anybody remember the derivative of 2 to the n? No one ever does. That's why I put this in here. So let's look at it. All right, it's really easy when you see it, but it's one of those we don't play with that a lot in Calc 1, so everybody kind of forgets it. So the numerator is just 2n, okay? The derivative of 2 to the n, right? Or let's just, I'm going to write it down here for you guys. So the derivative with respect to n of any value a raised to the n. So remember, a is a constant number. It's a to the n, natural log of a. So that means the denominator is 2 to the n, natural log of 2. Now don't get confused, that numerator is 2 times n, that denominator is 2 to the n. So a really common thing that you'll see is somebody will not be paying attention and they won't read their own handwriting right and they'll just say that those two things cancel. That's not true, okay? So we would in theory have to do L'Hopital again because we're still in an infinity over infinity situation. So if we do this again, well, the numerator just becomes 2. So ln of 2, remember, is a constant, so it stays where it is. But when I take the derivative of this again, I get 2 to the n, natural log of 2 again. So now I have 2 of them in the denominator, so it got squared. Well, now if I try to take the limit again, I've got a constant on top and infinity in the denominator. So it's clearly going to 0.